Mr. and Lady Chairman, just let me know when I'm in the last 10 minutes to make it shorter if I can. I'm coming from another ASHA chapter, European chapter. We called it Danube ASHA chapter because we didn't have in Serbia so many members of ASHA to fulfill the conditions to establish the ASHA chapter, so we united our efforts with Romanian colleagues, and so started we with our ASHA chapter. ASHA chapter is taking all the individual members from so-called Danube river countries, and I would like to mention, I'm very proud of that I was in ASHA delegation when was established this ASHA chapter. I would like to believe, that was many years ago, that I was in that moment in high school, say. I'm going to speak about the new technologies for a reduction of heating and air conditioning energy needs, and then I'll give some few examples. Namely, you know, new technologies and new practice always was new in that moment, you know. Even when we started to use insulation, that was the new try to have much lower energy consumptions. So I will give a brief history what was in some moments very new technology, very new practice. So I have here, now I don't know where to press, but I will see if I'm... Where is going that? Yes. We are all realized that the temperatures, especially in the summer seasons, are much higher than before. Here is average summer temperatures in Athens. You see how it's in the last 100 years increase in this average temperature. Where did I press here? Here is, for example, the problem which we have in Europe and in the whole world. Because when many of these buildings, majority of the buildings which are today existing in the world were not built then when we were taking care of energy like today. So you can see that in millions of square meters of the flats, how much was increasing the air-conditioned space. And that is a problem, you know. We can now make very efficient buildings if we are building today, or if we built last year. But what was with the majority of the buildings which were built 40 years ago or 50 years ago? When I started at mechanical engineering faculty, we didn't have it in Belgrade the air conditioning as a special course. We had the heating. But then slowly, if I could say, I established the air conditioning courses, what is now very obliged. Why we didn't have that before? First of all, the temperatures were, even in the winter time was much lower than today. In the summertime was also lower, but what's happening now? I knew that I would miss something. Yes. Here is some data from London. You see this blue column is presenting the rise of the cooling loads in the London city. So you see we have now in the last 50 years, it was now 25% greater cooling load than it was before, but in the same time heating is much lower than it was. I only remember when we started in Belgium to calculate the outside design temperatures. In the winter time was -20. Then a little bit later was 18, 16. Now we are calculating for -12. In the summertime was always about 30 degrees. We are still calculating with 33, 34 degrees. But in the same time, humidity is much higher than it was before. That is everything increasing the energy consumption, and I will here much more concentrate on the loads which we have during the summertime, because that's now very critical. Here is now in Belgrade, you know, in the 60s we started to air conditioning the spaces. We didn't have much air conditioning, especially in the cinemas, in the theaters, in such buildings, but in private buildings, in office buildings, we didn't have. And that's now, for example, one of the buildings where are located all our ministries. Now you see how that looks. And can you imagine now, during the summertime in July and August, when all that is, when we have the highest cooling loads during the summer, when all that starts to work and to operate. What an attack is that on our electrical system. So that is the main reason why we have to see what shall we do in the future, what we are doing today. For example, I will just historically go briefly what we have done concerning the lowering the energy needs. You know, during the summer we are taking the white clothes, very light, and then I was thinking it would be nice if we can change the facades to the general buildings. I found one that was in Chicago, but this building was not built to be so. That was one building which was repaired, and then they just protected from the dust the neighborhood. Of course, theoretically, that would be nice if we can change the facades when we are in summer or when we are in the winter time. We couldn't do that, but we can have a double facade, and in one moment that was very popular. The architects were designing such a buildings. But you see, that's a problem. If we have a double facade that is already dressed for summer and for winter. For winter, that is very useful because you can protect from the low temperature outside. And for example, here is one double facade in center of Belgrade. This double facade is also insulating the building from the noise from outside. But during the day we were making the analysis what would be the temperature between these two facades during the summer when we have, for example, south-oriented building and when we have a nice day. We saved a lot because the temperature in between will be much higher than it's outside, so the heat losses will be much lower. But what to do then during the summertime, for example, if that will be also south-oriented facade, what the temperature will be in between these two facades, of course much higher. So in that moment, in such occasion, we have to make some holes in this facade, which will be open during the summer, so the air will circulate. At least theoretically we could achieve there the temperature which is equal to the outside, not to be much higher, but always is higher. So that was in one moment, I would say, much more dictated by the architects, and I would like to mention here that we mechanical engineers dealing directly with the energy in buildings, we can nothing do if we don't have understandings from the architects. So we have always an international congress in Belgrade, which started 45 years ago, as I mentioned, when I was in high school. And then this time I invited 10 architects, but believe me, I got only answers, and they have papers only from the young architects, not for the older architects. So that's always some how can we say, collision between us and architects, but to be honest, without understanding of architecture, we cannot do much. Did you check that? I lost it. I was playing and then I went on the little. Okay. That was the first step how two architects were combining energy to save the energy. That was architect Crenshaw from Great Britain, and he made the project of for the World Conference, World Exhibition, which was in Spain, I think in 60, 70 years, century. You see, the water was flowing above the glass facades. So there are several, how to say, goals which he has achieved. One is visually the sun is coming and shining on this glass. The second one is that we have a cooler temperature of the glass outside, so that is in some way reducing the cooling loads, and also that is one how to say protection from the solar radiation which is coming through the window. So upstairs we have hats which we are using when it's very hot weather, which are movable depending upon the solar position. In the same time now we can use that, and there are a lot of examples such that this is combined with the photovoltaic solar panels which are absorbing the energy and transferring into the electricity. I get totally lost. I don't know which side I have to look. Maybe to go there, here, come. Okay, we were measuring mechanical engineering faculty in Belgrade. What is happening when we have such a facade where is flowing the water, and we found that there are many reasons why not to accept and use. First of all, we are using a lot of water. Can you imagine there when we don't have much water, and when we have such influence of solar radiation, you cannot use because there's too much water. Then we found that the glass towards the water is not how to say philic to the water. We call that hydrophilic. It's much hydrophobic. It's against. You see that the water is not distributed well on all the sides. So somewhere you have a thick layer of the water, somewhere you have a thinner layer of the water. So we found that that's not very useful. We do not recommend that. Here is again another building which I showed to you, which was done for the World Conference exhibition in Spain. On the side, you can see that there are like flags, like curtains from some material through which the water is flowing slower, and then this water is evaporating and making the temperature toward the glass behind this facade is much lower. So that were in that moment some new, how to say, practice, some new recommended protection of the solar cooling loss. Now we have another kind of double facades which can be at the same time covering and protecting the facade from solar radiation. In the same times that could be, and they have done in the practice, that could be combined with the collection of the solar, like panels for photovoltaic. And now we are coming on something new what I have privilege to find in the journal Energy and Buildings, for which I'm still editor, and a lot of papers what I have found are just thinking and treating this problem which I'm now representing. You see, now they are using they are coating. That was the first paper was from Japan. They are coating the facades with the titanium dioxide, and they are covering the facade with this liquid, and has a lot of privileges. First of all, when we are now using the water to flow above the facades, this angle between the water and the surface is now nearly zero, what means that the water is totally very fine distributed upon the facade. So in this case we are using much more water if you would like to use water to cool and to reduce the cooling loads. So you see, this titanium dioxide has a lot of how to say, qualities. And for example, I heard, I didn't know that for example in Japan they are producing now the cars which are coated with titanium dioxide because it's anti-fogging, you have another fog, it's self-cleaning and a lot of good characteristics are. That is now what I found in one Japanese article. I'll give on the next slide the authors who have done that. You see, they distributed this water upon this coated with titanium dioxide emulsion facade. And then in the blue you have the water where it's distributed, the red is collecting the water. And then this thin layer of the water is flowing down. So we are not using so much water as before in this first example which I showed to you in this paint. And now down you have, why I'm always touching that, never mind. And down you can use this to collect the water which was flowing, which was not evaporating, so again to recirculate. And then this water is not so much used as if that would be like in the first case. They have done some simulations, and here on the left side you have a building which was not coated with coated facade. On the right side we have it coated, and you see that in the maximum temperature during a day, it was without coating 41 degrees the temperature of the surface of the facade, and here was 10 degrees less. That is a great benefit, especially during the night, because all that what was absorbed by facade during the day is just back radiating, and the temperature of the city in the streets is much higher than it should be. So that is a very interesting try. But now I would like to see the analysis how much the coating is expensive, what you are using, how much work it costs, and do we have on the end benefits. But one day, when the energy will be even more needed as today, each price would be much cheaper than the price of the work. I will just mention today that I found in the library of my grandfather, that was a book which was had a title "War for Petrol," that means for gasoline. And everything that's happening today was described in the 1934. So many details, I was laughing or crying when I read that. Now we are coming on the last, what is today very actual, that is use of fast change materials. That's, believe me, each third or fifth paper which we received in this year for the Energy and Building Journal was mentioning and treating the fast change material. So fast change material, you know what is that? A substance with a high heat. So, heat of changing the phase when it's melting or solidifying. Heat is absorbed or released when the material changes from the solid to liquid. And there are many cases how we can use these fast change materials. We can use it just to shift the cooling loads in the better time, so to store the energy during the night when the material could be solidifying, and during the day could be then neglect the heat gains. But there are, of course, as usual, always many other difficulties. Fast change material has to be cheap. Fast change material has to change the phase in the range of the temperature during the day when we are cooling. That means between 18 and 38 degrees during the day. So that is number one. Number two, the problem is if you are using fast change material, in one moment this material can be liquid. And can you imagine if you are combining that in the wall, in the mortar, or in some another material, in one moment that will be liquid. So now the new step was that we had to put that in the capsules, so we call it microcapsulated fast change materials. That is now technology which is not in the how to say, the field of us mechanical engineers. That's now for the engineers of technology and chemistry. So, but this material has to be cheap. It has to have a very great latent capacity or latent heat when it's changing from solid to liquid and vice versa. Then, not after many times repeating this process, not to lose the characteristics. Can you imagine we build a house where we use this fast change material as encapsulated in the mortar or in the walls, and some after 10 years that's not anymore functioning how we had thought it will be. So that are many problems, and believe me, many centers in the world are doing that, because in the moment we don't have any idea which would be better.
Mr. Todorovic, 10 more minutes.
Oh, 10 more minutes is a long time. Encapsulation, I said, why is not? Okay, I have no idea what's doing there. Okay, that is that are the encapsulated fast change material. On the right side, you see that is the size is 5 microns. That means 1 micron is 1,000th of 1 millimeter. Can you imagine how that is small? The first time I saw that in some liquid when I was in Hong Kong, it was the defense of one PhD doctorate, and then it was something like a yogurt or like a milk or something. I said, excuse me, is that fast change material capsulated? They said, yes. How you have done that? Then the professor who was the president of the commission said, excuse me, we cannot answer that. That is a secret of our laboratory. I said, excuse me, but then he invited me from Europe to come to put the questions to the student. So he can always answer, it's a secret of our laboratory. Here is now capsulated on the right side. You see it's combined with the plaster of the wall. So we can fulfill, for example, the holes in the concrete with the encapsulated fast change material. And then, I really don't know. Sorry about that. It was measured, for example, you see this blue on the upper picture. You have this fast change material that was one montage building or like a garage, and they were trying to see how much they have done. Anyway, they have found when they were measuring that in combining with the very good insulated roof, you can only add 10% more efficiency. So it's not to say now we save 50% of the cooling loads if we are using these slabs on the roof. Only 10% more than if it was classically insulated before. Here is now, if you are using the fast change materials in the buildings, but here I made again a mistake. Anyway, I don't know what's happening. Here is now a combination of the fast change material. That's an active system, not anymore passive. Passive system would be, if you saw the one picture before, there was slabs, and then during the night the fresh air from outside is cooling these slabs where is the fast change material. Tomorrow is flowing the real air, or the solar radiation is falling into that, and then it was used, the energy which was stored during the night when the temperature of the air was, say, 18 degrees, what was the minimum during these 24 hours. Because I told you that fast change material changing the phase just in the range of the daily temperature. Here is now combination with solar radiation during the day that can be used for heating during the night. It's because sometimes we don't have a solar radiation, then it has to be helped by the heat pumps. And here I will just jump on that because that is something, but I will not have time to mention something, but I will. Here is, for example, the windows are the weakest point of the envelope of the building concerning the energy. And then there was developed and there was a lot of laboratory investigation. If you have double glass window, to put fast change material between these two glasses, what we can achieve. Here was one PhD done in England. I'm proud to say that was one Serbian girl doing that in London for her PhD. You see, if you have some fast change material in the first picture, that is standard double glassing, and you see this blue square is just what you see through. But then, how is that changing the phases? Then you see, for example, in the second, you have this mushy picture, because the light is not going transparent so good as before. And now, on the light, on the right side, you have a fully solid. Can you imagine now, if you have a low temperature in the night, you don't see anything through the window, but during the night we always have some jalousies, and we don't have so good view through the window. But still, that's not how to say one satisfaction to be used, but we don't have any other source.
5 minutes.
If I finish before, I'm getting some coffee as a word.
You will have any questions? Probably.
I just wish to say that during these changes of the phase, the window is transluted. So that means you cannot see much, but sunlight is coming. Generally, when you are reading the results of the factories which are producing, they said that in the best moment you have 40% transparent for light. If you agree, I can finish. Thank you very much.
Thank you. Are there any questions?